Hey there, and welcome. Today, we're going to dive into a quiet little puzzle that sits right at the heart of how computers understand language. It might sound super technical, but it's really about something fundamental. How do you give instructions that can only be understood in one single way? So let's start by taking a closer look at one of these puzzles.
We're not going to start with an answer. Instead, we'll start with a question centered on a line of code that looks really simple on the surface, but actually hides a tricky little trap for a computer. So take a look at this. A human programmer, you or me, we might glance at this and probably guess what it's supposed to do. But a computer needs absolute certainty. It can't guess. And when it looks at this, it sees a problem, a fork in the road. Which if does that else belong to? The first one or the second one? That's the mystery we need to solve.
To get to the bottom of this, we have to remember that you can't just talk to a computer like you talk to a person. You have to give it a really precise, formal set of rules for a language. The best way to think about it is like a blueprint, right? Before you build a house, you need a detailed plan that shows exactly how every single piece fits together. For a computer, this blueprint is what allows it to understand our instructions. And this blueprint for programming language, it has a name. It's called a grammar. It's just a set of rules that defines what is and what is not a valid statement.
Now, what's so cool about this slide is how simple these rules can be. This here is a context-free grammar for basic math. The rules just say an expression can be made of other expressions and operators, or it can just be a number. These few rules are recursive, which really just means they can refer back to themselves. And that simple trick is powerful enough to describe pretty much any math you can think of. Okay, so using that grammar, a computer can take a line of code and break it down into all its little parts, organizing everything into a structure. And this structure has a name. It's called a parse tree. It's kind of like diagramming a sentence back in English class. The tree shows the exact structure and meaning of the statement, all based on the rules of the grammar.
But what happens when the blueprint isn't quite as clear as we thought? What if one set of instructions can lead to two different, totally valid structures? Well, that's where our problem really begins. So let's circle back to our if statement. The problem is what's called the dangling else. See, the grammar for a lot of languages says that an if statement doesn't have to have an else part. It's optional. And believe it or not, that one little optional rule is enough to create all this confusion.
And this slide just perfectly illustrates the problem. When the computer follows the grammar, it doesn't find one way to structure the code. It finds two, and both are perfectly valid. Take a look at the tree on the left. You can see the else is attached to the inner if. Now look at the tree on the right. Here, it's attached to the outer if. Both of these are technically correct according to the rules, but they would make the program do completely different things. This, right here, is ambiguity. So, now we can finally put a formal name to it. An ambiguous grammar is any grammar that allows a single string of code to have two or more different parse trees. It just means there's more than one valid way to interpret the instruction.
And this isn't just some academic thought experiment. As the source text says, it's a really serious problem. A computer can't just pick one. If the structure isn't precise, the meaning isn't precise, and the program just can't be reliably translated. The computer is basically stuck. So the most important thing is that we have to resolve this ambiguity. We have to give the computer the clarity it needs. And it turns out language designers have two main ways of doing this. So there are two main approaches here. On one hand, you can rewrite the grammar itself. You make the rules more complex and specific to just get rid of any possibility of confusion. On the other hand, you can keep the simple, ambiguous grammar, but give the parser a little external rule to follow when it gets stuck. For our dangling else problem, that rule is usually always attach the else to the nearest if. Both paths get us to a single, clear answer. And here's a great example of that first path, rewriting the grammar. To make sure we get the order of operations right, the grammar is split into different levels for expressions, terms, and factors. This structure makes it totally impossible for the parser to build a tree where addition happens before multiplication. The clarity is literally baked right into the blueprint. So which way is better? Well, there's no single right answer. It's a design trade-off. Rewriting the grammar can sometimes make it way harder for a human to read and maintain. So a lot of the time, language designers actually prefer to use a simpler, more elegant grammar and just add that one extra guiding rule to solve the few confusing cases that might pop up. All right, let's zoom out for a second and just bring this all together. What's the key idea to take away from all this? So, what have we really learned here? First, that ambiguity is just what happens when one instruction can have more than one valid meaning. We also learned that this is a huge problem for computers because they need absolute certainty to do their job right. And finally, we saw that we can solve this, either by writing clearer, more complex rules from the very beginning, or by just giving the computer a simple tiebreaker rule to use when it gets confused.
And in the end, this little journey into how compilers work, it really reveals a much bigger idea. In language, in code, in pretty much all communication, ambiguity is always going to exist. The real goal isn't to create a world with no ambiguity at all. The goal is to recognize where it might show up and to resolve it thoughtfully and with intention.